On page 449, section 13.4, there's a whole section that will be on the test. Concepts, there'll be one problem at least. And basically, if you think about a spring, let me get a pen here first. Think about a spring, and I have a mass M on the spring, and there's a spring constant K, and I pull down. So this is equilibrium right now. I pull down on the spring with a force F. When I do that, it begins oscillating up and down, up and down. And if we could make a drawing, a graph of the oscillation, it would look like this top graph, kind of sine wave-ish. It's actually a cosine. And we know that x, that's the distance it's stretched from its equilibrium, equals a, that is the amplitude, that's the largest, that's when I pull it down. And let's say that I pull it down to right here. Well, it's going to oscillate up and down about the same height from the equilibrium, and we call that distance from here to here the amplitude. A, that's the maximum x distance. It can't go bigger than that. In real life, it gets smaller and smaller. That's called dampening. But if we ignore friction and air resistance, this thing forever goes to A and then back up and goes up here to A. That's supposed to be an A for amplitude. And just oscillates back and forth, back and forth, back and forth. I guess I really need to make this spring go up here. And it'll just keep going back and forth forever and ever if we ignore friction. So at this point, t over 2, it's got its maximum. That's when it's at A, negative A, and then positive A when it's at t, because we started at A, the largest distance, when it was at t equals 0. And it continues on. Well, if I take and so this is the equation right here is the equation. I don't think it's on your equation sheet, and you'll need to know it. And this omega here is called the angular speed, and basically omega equals, and you can look this up in the section, equals 2 pi over t, or it equals 2 pi f for frequency. So if I take the derivative of this, and you don't have to know how to do calculus, I'm just doing this for the benefit of the people that know calculus, because then you don't have to memorize as many equations. If you take the derivative of this position function, you get the velocity function that looks like this. V equals negative omega A sine omega t. Again, omega is 2 pi over t, or 2 pi f. T is time, by the way. This little t here is time. Take this second derivative, and I get the acceleration equation, which is negative omega squared A cosine t. Let me undo that. I kind of covered up the equation. So here's the interesting thing. See this dotted line? When the velocity is at its max, in other words, it's moving as fast as it's going to move, the x position is 0. So when this thing comes back to its equilibrium position, and this isn't really the symbol for it, but we'll call this E for equilibrium. How about EQ? Then it's moving the fastest right here. When it gets way up here to A, its acceleration is 0. That means its force is 0. When it gets way down here to sorry, I said that wrong, I think. When it's at equilibrium, it's got the largest velocity, and there is no force and no acceleration. When it gets up here to A or down here to A, it's got its largest, because see, when it's at A, let's just take right here, and if you just go down, that's 0, but this is max. So it's got a 0 velocity at both ends, at both A's. This would be positive A, and this would be negative A. Down here, that looks like a theta. And so as long as you understand that's a negative, I'm not drawing very good today, very well. Anyway, so when you get down here, it stops. It has its largest force, its largest acceleration. Here it's got its largest velocity, zero force, zero acceleration. Its displacement is zero. And so with these equations, if we know frequency, then at any time t, we can find its position. At any time t, we can find its velocity. At any time t, we can find its acceleration. So read over that section and be sure and know that section, and it will help you on the test, the semester test.